weather code. As I said, it's the second webinar of a series of 2 webinars. We had a first webinar last week where we presented 5 projects already, and today we present another 4 projects another 4 projects who are part of ECMWF Summer of Weather Code this year. Before we present the projects and also the teams who are work on the projects, I will just give a short overview of what ESoC is about and who is organizing it, and also how you can engage today and ask questions. And then we jump right into the project presentations, and also the teams have opportunity to present themselves. So ECMWF Summer of Weather Code is a online program which is organized each year and which offers coding challenges and coding projects for a period of four months over the summer. And each year we invite teams to team up with mentors from ECMWF and Copernicus to work on open source code and developments related to climate, weather, and atmosphere. And Summer of Weather Code, it's organized by ECMWF, the European Center for Medium Range Weather Forecasts, and also supported by Copernicus, the satellite program from the European Union. And how ESoC works, so it works that, this is just an example how it worked this year, but the timeline is usually always similar, with opening up the applications at the beginning of year. So each January the applications open and they will close around April, so mid-April or end of April. And then the teams got selected and are announced 1st of May. And this is usually also the start when the coding period starts. And the coding period is usually between 4 or 5 months. This year it's 5 months. It started 4th of May and it will end 30th of September. So all the teams are now around 2 months into, or 3 months into coding. They have opportunity to present their project today and also their preliminary results. And then they have another 2 months of coding until the final projects and results are presented on 16th of October. And this is another opportunity where you can join when you're interested. This is a day dedicated to the ECMWF Summer of Weather Code outcomes this year. It's 16th of October. But at the end, I will share some more information. And yeah, this is how ESoC works. As I said, we already had, so this year we support up to 10 projects. Unfortunately, one project didn't have the opportunity, or doesn't have the opportunity to present last week and this week. But last week we already have 5 projects. And if you're interested and you couldn't make it, you can go to YouTube, to ESoC's YouTube channel, and watch the recording of last week's webinar, where 5 projects mainly related to machine learning were presented. And today we have another 4 projects which have the opportunity to showcase their, to tell us what their project is about, and also to tell us about their preliminary results, what they've been working on the past 3 months. And I'm very excited to let you know that we have today as the beginning project Ayush Prasad with the project creating Jupyter-based open IFS training material. And then as a second presentation, it will be Tiberiu Lepadatu, who will present his project on HPC performance profiling tool. The third presentation will be given by Mohit Anand and Kumar Sridhar, who tell us about their project on detecting anomaly in air quality stations. And the final project will be Milan Klöver presenting his illifridge.gl project. And with this, Before we start, I just would like to point you to slido.com. So please go to slido.com and enter the hashtag ESoC_AMA, because this is the opportunity where you can ask questions to the presenters today. So you can ask questions to the projects, but also to questions related to ESoC in general. And given the timing, we will probably, after each presentation, we will probably have time to respond to 1 or 2 questions directly if there are questions on Slido. But then after all presentations, after the 4 presentations, we will have a dedicated Q&A session where we will go through all the questions on Slido as well. So please go to slido.com, enter the hashtag ESoC_AMA and ask your questions about the projects and ESoC in general. And with this, I stop sharing my screen. And I would, hang on here, and I invite Ayush Prasad to share the screen and tell us more about creating Jupyter-based OpenIF as training material. Ayush, the floor is yours. Thank you.
Yes, so hello everyone. My name is Ayush. I'm a third-year computer science undergraduate studying at Sikkim Manipal Institute of Technology in India. My mentors are Olivia, Michael, and Adrian. So my project is about creating a Python interface for the OpenIFS, and then using that interface to create training materials for the OpenIFS models. So before moving on to the actual project part, I would like to give you all the brief introduction about what OpenIFS is. OpenIFS is a weather prediction model, which is more easy to use and more easy to use and slightly easy to operate version of the integrated forecasting system, which is used at ECMWF. It has many of the same capabilities minus the data assimilation capabilities. OpenIFS is predominantly written in Fortran, and it is configured using a set of name lists in which different variables are configured, such as the dates of the model run, input directories, etc. So to currently use OpenIFS, the users have to perform quite a long steps. Some of them are, first step is to install the OpenIFS binary locally. This requires all of the prerequisites to be fulfilled, such as the compilers and the other uh, environment variables and the other APIs to be set up locally. Next, the initial data has to be downloaded, which would be sent to the OpenIFS. This consists of the name lists and the initial conditions. Then if the model's performance has to be evaluated, then we would also need to download the reanalysis data from the ECMWF servers or through any other way. Next step is to configure the working directory. We copy the files which are created in the previous step, and then we place them here on the working directory, and
Okay, I think Ayush had some connection problem. Let's wait for him to reconnect. Here we go. He's back, yes. Ayush, we can now see you, but we cannot, you need to unmute your microphone. we go.
Is everything? Thank you. So as I was saying, this entire steps which have to be performed are very manual. And the major challenges of doing this is that each one of them has to be done in a separate window, and they require the user to focus on the actual configuration parts. So why should we create a Python wrapper and use Jupyter notebooks when we already have the OpenIFS binary? One of the major benefits would be of using a Python wrapper would be that it would increase the use of usage. Now, Fortran is a very good language for running weather models, but new users might slightly find it better, or may benefit from a higher level of abstraction which the Python wrapper could provide.
Hi,
Next.
sorry, Ayush. Can you, I think you're not sharing your screen.
Oops.
Probably when it disconnected before. Here we go.
Yes, so what I was saying is that why should we create a Python wrapper and use Jupyter notebooks? So main benefit would be to make the process more interactive and easy to use. The third benefit would be it would allow the users to focus more on the actual science behind weather forecasting instead of spending their time in setting up environment variables and downloading data and then linking that. And it would be much more beneficial for everyone if they focus more on the actual science in the initial stages. And finally, it would make it possible to create a containerized access to the OpenIFS. Now, the advantage of this is that we can then deploy these notebooks on any server. For example, as a part of this project, we have planned to test this on the European Weather Cloud, but this could also be expanded to many other such servers. And later on, it could also lead on to the possibility of providing OpenIFS as a service, which that platform could be, which could be beneficial for many other use cases as well. Now, as a now for this project, for one of the first use case is to run the Desmond 2015 Desmond case in the Jupyter Notebook environment. So for doing that, the existing method, like I said, is to first to copy the initial conditions to working directory, setting the environment variables, and then the names have to be downloaded and they have to be edited. And as you can see here, these are the different variables. This is the time step of the model, and this is the number of processors used along with other such variables. Then the fourth step is to run the model. Now, as I said, the major disadvantage of this existing method is that in the initial stage, it would require users to switch between many windows, and that would not be a very good use of their time. In the ESoC 11 way, we are proposing and have developed the initial prototype to run the Desmond model through a Python function. Now, as you can see in this Desmond function, we are providing the time step, the processors, the number of thread used, and other such variables through a Python function. Underneath this Desmond FC function is the IFS bench package, which is being developed internally at ECMWF. The IFS bench package reads in the name list via the F90 NML package, and then it converts those to usable Python variable types. Then after that, it does not just convert those to Python variables, and it also executes the model, and it also has the capabilities to benchmark the outputs. As a part of this project, we are also expanding this IFS bench package so that it could be used for many other use cases in our project. The next step after the models are in is to visualize the outputs. Now, again, on the left side, you can see the existing method, how the outputs are visualized using MetView. Now, in MetView, the plotting can be done in two ways. The first step is using the interactive tool, which is actually a very good um, way to visualize the outputs. I personally benefited a lot in the initial stages. And the second way is to use the batch mode using the METView macros. Now METView has a internal has a programming language, which is a very powerful way to use all the capabilities of METView, and it provides many other such features. Now again, the main challenges of using this existing method is that both of these METView visualization processes require the the steps to be done in a completely different workflow, which is not very beneficial in the starting stages. And it would be very nice if the person who is learning can simply visualize in the notebook himself. So in the ESoC 11 way, we are again using the METView Python bindings, which is a relatively new tool which is being developed at ECMWF. Now, METView Python is built up on top of the Xarray and NumPy and Pandas and many other such Python libraries, and it also adds its own features so that the entire existing METView can be accessed using a Python interface. Now, using this, the visualization can be done in Jupyter notebooks. This is one of the example plots which we have created using the of the Desmond case. Many such, this is a temperature plot for the October 15th, and many such plots are available on a Jupyter notebook in the ESoC 11 repository on GitHub. The next step of extending the visualization is to use the METView macros, which are currently used for comparing the results with the reanalysis data and to convert them to their Python equivalent, so that we can also compare the reanalysis data in our Jupyter notebook. So these are the broad next steps which we have to take. First step one is to extend the configuration options. Right now, the configuration options for the using the Python IFS, Python OpenIFS is very limited. We are just able to configure the number of processors, the number of dates, the latitude, longitude, and we would like to extend this to furthermore configuration, so that everything can be done through the Python interface. The next step is, like I said in the previous slide, would be also to translate the existing METView macros to their Python equivalents, so that the reanalysis data can be visualized in the notebooks. And finally, our major end goal of this project would be to use Jupyter notebooks and deploy them on Jupyter Hub, which would allow everyone to use a single server. And so whenever people in a workshop or anywhere else in the initial stages can simply log on to a server and then run the OpenIFS there itself without having to download anything on their computer, which would, I believe, would be a very helpful step. And we would also like to test this on European Weather Cloud. You can follow our progress on GitHub, and it would be very nice if you all can provide us some suggestions so that the usage can be improved for everyone. That's it from my side. Thank you.
Thank you, Ayush, for presenting your exciting project updates. For time reasons, I would just continue to the next presentation, but I remind everyone you can go to to slido.com and enter the hashtag ESoC_AMA in order to ask your questions. And now I would like to invite Tiberiu Lepadatu to share his screen and tell us a bit more about your project about HPC performance profiling tool. The floor is yours. Thank you.
Okay, I'm starting the video as well. Can you see me and hear me? I hope so.
Yes, we do.
Okay. Hello, my name is Tiberiu Lepadatu. And today I'm going to talk to you about the high performance computing performance profiling tool that I've developed in the last few months with the help from my mentors, Olivier, Michael, and Clark. Firstly, why do we want to create a profiling tool? Of course, there are many profiling tools in the IFS that people use. But as Ayush has already told you, IFS is a very big and complex project which has thousands of routines and subcomponents, and they are very different in the view of performance characteristics. So to understand these performance models, these characteristics that HPC in a very complex system, it's very complex for an engineer. So even though there are a variety of built-in performance measurements, we need to aggregate them, and I'm going to show you in the next few slides some raw data, and you are going to understand why the raw data are not good enough, and this project is really important. The aim of our project is to make a way of presenting the data in an interface which presents the data in a way that people can understand, can comprehend very easily. Also to use try to have a comparison oriented view in respect of the data, and also to understand which impact small change in the code has on the IFS code base. Also, we really want to have all the data available everywhere. So by having a dashboard, a web-based dashboard, we can access it from any device. And it's very important to me and also to my mentors that the interface is very flexible and extendable. So this is the wall of text that the HPC profiling tools give out. You can see here that is the total number of seconds that we have for a routine, here the total number of calls. But it's very hard to understand which are the main outliers or which are the outliers of the run, and how your changes to the code has impacted the performance of the IFS. So we are proposing something much easier to understand, interactable and graphical interface that you can see here directly the relationship between these two routines. As value here, we have the total time that you can see in here, and everything is very simple, and you can see just by one view every data that you want. So basically we are transitioning, we are trying to make this into this and into many graphs. What have we done so far? We've analyzed many benchmarks tools. For example, we've analyzed Scalaska or iPerf and many others. And we've looked there to see which are the most important ways of visualizing data. Then we've created some initial plots in the Jupyter Notebook that I'm going to show to you in the next slide. And then we've started playing with the layouts of the dashboard. And in the end, we've implemented a server that it's acting as a proxy between what we have done in the Jupyter Notebook and what we have on the dashboard. So we are practically just calling out all the methods from Python, from the Jupyter Notebook, into a very beautiful interface. We had a lot of challenges along the way. First of all of the plotting libraries have a different way of saving the output. Some of them use HTML, some of them use SVG, some of them use JPEGs, and so on. So it's very hard to make a tool that's a hammer that can strike them all, let's say. Then it's very hard to call Python functions from JavaScript. So we've abandoned this idea. We have made something, an artificial way of calling Python functions. Also, Plotly has a very weird way of saving HTMLs, and one of the biggest problems was that the final output of the project should be configurable from Python. And Python has a very, let's say, rough around the edges way of creating interfaces. For those of you who have played with it, you know what I'm talking about. So this is what I've done in Jupyter Notebook. This is the custom spider graph. Why is it custom? Because you see here the DPOps, or the floating point operation executed optimized to count, scale, double precision vector operations, goes from 6,100 and something to 9,099. So very big numbers, but the time goes from 6 to 9, so single digit number. So we've done something to be able to see all of them on the same graph. So it's this graph doesn't come from any library, it's done by us. It's something really special to this project. It's kind of awesome in my opinion. So yeah, so we took this graph, this awesome graph that we've created, and we just call it from the React interface. So everything just goes from here into here in some simple steps. You just have to configure a JSON file, and that's all. So this is the flexibility that I've talked to you about in the first slide. What we want to do in the future, we firstly want to stabilize the server and the front end. We want to take your advice on the front end, your tips on how the front end should look like. On the part of stabilizing the server, we are talking about what can be calculated on the server and what should be calculated on the front end, because for us, interactability, the possibility to interact with the graph, it's a very high priority. Then we want to implement authentication on the server so that your configuration of the dashboard can be saved and you can come back to it, or maybe you can share it as well. Then we are going to create a Docker container for the application and to let everybody test it out. And in the end, I want to make a guide of how to create new metrics and let you guys hack my application to make something new out of it. What's important, what are the takeaways, in my opinion, are that we want to make an application that it's very easy to use, extendable. It's language and framework agnostic, because we don't want to care if you are going to use matplotlib or plotly or anything else to generate the plots. And also, we want to make a very easy tool to make sense of the data, the performance data that the IFS gives out. Thank you very much for your attention, and I'm waiting for your questions. Okay.
Thank you, Tiberio. We actually have one question on Slido, which we can address now. Is your profiling tool or framework adaptable to other projects other than the IFS? How intrusive or easy to profile a separate project is it?
Well, what I'm doing right now is creating an interface in React, and you are just calling from there. You are calling some server functions through a REST API. Actually, I have a photo if I can show it to you very fast. So wait a second. Share screen, desktop 2, I think. Okay, share. 1 second. I'm going to show a picture of the architecture that I have on the right now, so it will be very easy to understand. Okay, so this is the architecture that I'm using. I have here a Python server and a Python proxy. So if you want to implement the performance tool in your application, you are just going to write the server because the client is already written. So you are going to write there what performance tool you want, what performance metrics you want, and how do you want your graphs to behave. So it's pretty simple, pretty adaptable in my opinion.
Okay, perfect. Thank you to Berju. And then for other questions later on, we can then address in the Q&A session. So now I would like to invite Mohit Anand and Kumar Sridhar to tell us more about their project on detecting anomaly in air quality stations. So Mohit and Kumar, the floor is yours.
Yeah. Hi, everyone. I think you can see my screen.
Yes, we do.
Yeah. So today I'll be presenting on detecting anomalies in air quality stations, on which we have been, I and Kumar Sridhar have been working for last 3 months. And I just finished my master's at ETH Zurich, Switzerland, and Sridhar is just finishing his master's at Germany. And our mentors were Johannes Fleming and Miha Risinger. But I'd like to start with giving an introduction to the challenge that we had at hand. And monitoring air quality is always of prime importance because it helps us to understand the process, which leads to modeling the process. And in the end, it also helps us to predict different air pollutant concentration of air pollutants. And in the last few years, there have been a really sharp rise in the amount of data that is present online related to air quality measurements. One of such repository is OpenAQ measurements. They have more than 594 million measurements from different sources spread across 93 countries. And for comparing how these data sets are, how usable they are, we also have some of the data from the CAMS, which is a model graded data output. I'll just quickly jump into the air quality data of OpenAQ. We have such a large amount of data, but the major problem lies in to analyze what is the quality of the data, how can we use it, maybe to understand, maybe to use in some modeling. And there are some issues with this data. They have been using improper naming conventions. I think this is changing with time. Now they mostly use a 7-digit alphanumeric code for each of the locations. Earlier, the data that they had was spread in different languages, some in Hebrew, and then we had the problem with those languages was if there is a string containing latitude, longitude, everything was reversed. So in a way, we had to manage through that. Many a times there are inconsistent time series. These are the locations at which the data exists. And this is India. And what we see is that data exists in February 2019, and there is almost no data in the month of March 2019, while again in April, we have lots of data. So these types of inconsistencies were present in the data. The other challenge we were facing is we had a very large amount of data, roughly 500,000 data points daily, even more than that at times. And these data sets, since they come sequentially, they are arranged in time, but not spatially. Like one big file might contain the data sets for different locations. And this also led to some of the challenges that we had to face. Now, moving on, this plot shows the availability of the data, the OpenAQ data. What we did is we created a 0.75 degrees grid and calculated the number of stations on one particular day, that in one particular month, that is July 2019. And what we see on this axis is number of, the color shows the number of stations per grid. So we see a high density of stations in parts of China, Europe, and US, and even in some bigger cities in India. And this is just for PM 2.5, but what we are analyzing, we are doing this analysis for 4 different species. That is PM 2.5, sulfur dioxide, nitrogen dioxide, and ozone. And at some places, especially in Europe and some parts of China, we did see that there are many number of stations, like more than 30 stations per grid. But then we come to other parts of the world, maybe in Africa, and we see almost no stations. And just to give you the taste of how this data looks like, what we did is, this is a maximum PM 2.5 concentration on this day, but last year. And we see that there is a large concentration of PM 2.5 in parts of India and China. Average range maybe less than 100 microgram per meter cube. So just to give you how the CAMS data now looks like, CAMS data comes from a model and it is continuous in space. And what we see here is we have very high values, but they are just desert areas, or if there is some biomass burning. While on the other hand, on the different areas of the world, the CAMS data does really good. Here is one of the features that we can see is in these areas, what we see is,
I'm sorry, Mohit. Can you try to reconnect? You're having like
concentration, and there is a sharp change here. Is taking into different topographical. Sorry, yeah. Is it fine now, or do I?
Yeah, we're having this. It's like you're like.
Hello.
Yes.
A second. Okay, I'll quickly try to reconnect as well. Yeah. Hello? Should I? Just a second, I'll try to reconnect.
Okay, I can hear you now.
Okay. Maybe just switch off the video. Yeah. And yeah. So I'll start. Yeah. So
Yes, we can hear you.
yeah. So these are the PM, as I just said, like these are the number of grids, number of stations per grid, which is scaled here from 1 to 6. And we see that there is high density or high number of stations per grid in parts of China, Europe, and US, and some major cities in India. At some point, some of the grid stations were more than 30 even. And while I show this for just PM 2.5, we are looking into 4 different species, namely PM 2.5, sulfur dioxide, nitrogen dioxide, and ozone. And this is the plot of maximum value of PM 2.5 on this very same day, but 1 year before, like 2019, 29th of July. And what we do see is that in India, we see some of the values which are really high. In parts of China, yes, some of the values are really high, but in the other parts of the world, especially US and Europe, the values are not that high, and maybe they are well below 100 microgram meter per cube. And just to give you the taste, this is of the CAMS model. This is a model data, and we do see very high values of PM 2.5 concentration in maybe desert areas, or maybe in the regions where there is a biomass burning. But on the other hand, we do see that this model is very well able to capture the difference in concentration, maybe due to topography. What we see here is the mountain range, the Himalayan, and we see that there is a sharp decrease of 5 concentration in the mountain range. So our approach was, how to find the outliers, or in a way, how to find the stations which maybe are not giving very good, or maybe are not giving the correct output. So what we did is we created a 15 days window. Say we go to one of the particular month, January, we take the 15 days of January and then try to plot that data concentration based on, dependent upon the duration, time of the day. Concentration based on the time as a Gaussian processes. And then we create a confidence interval of 3 standard deviation that try to find out the points which are lying outside this 9.7% confidence interval. Hello. Yeah. So, and what we do with these points is, in a way, we try to penalize our process based upon these points, the points which are really out of 99.7 degree confidence interval. Things clear on the next slide with the pictures, but just to give you a slight overview, and this is how we penalize these points which are outside the 99.7% confidence interval. And the advantages of using this method was that this is independent of time of reading. Not on every day the data should be read, noted down at the same time, which is at many of the stations. The temporal length of the entire time series can be of coming slides. What we do see here is these are the PM 2.5 concentration in January 2019 near Beijing, and we see, and they for this deviation which lies from here to here. Now we do see that for the 15 days in January at a particular location, we have 11 points which lies outside this confidence interval. So what we do to penalize, to kind of create a score for these points, is we calculate the distance of this point to the the mean of the predictions, this red line. We calculate that distance divided by the mean of the predictions, that would be this distance. Why do we do that? Because in different cities, the kind of mean concentration might differ and we want to normalize. That's why we divide this outlier, the distance of this point from the mean, divided by the mean of that mean lying on the same time point. We do this for all these points and then sum them. The important here is these points will contribute more to the score because this distance is large compared to these points where this distance is small. One year of data, what we will have is total 24 such plots, and from each of them we calculate the score and in a way average them, and thus we provide a score. Now this is the same PM 2.5 concentration for 15 days in mid-April
we're having
near
the same
London.
problem now. Like, it's really
What
lagging too much. Can you hear me?
Is here, first the PM 2.5 concentration is way lower. We do have some high values, but they don't fall above the 9.
Are you still there?
Hear me? Yeah, I'm still there. Hello?
Okay, yeah, still having some lag problems.
Yeah, I'm trying again. Problem? Okay, maybe. I'll try to. Hello?
Yes, okay, I can hear again. Yes.
Yeah. So yeah, this is one of the plots for 15. These are the 15 days data of PM 2.5 concentration during different hour of the day for one of the stations near London. And what we see here is that all the values lies in 99.7% confidence interval. And thus we would not require to penalize any values. What also came here is, while analyzing this data, is we did two similar plots, where on x-axis we have the hour of the day, and on the y-axis we have PM 2.5 concentration. And this is in mid-April, like 15 days in mid-April. And and this data is taken from a station near Delhi. What you see in
Mohit, excuse me,
pink
could
is the
you try to
2019 data,
restart your
and we
screen
see
again?
way higher values, and even the 99.7. Yeah. Okay.
No, unfortunately,
Yeah.
we didn't see anything.
Okay. Like now you can see it, or now you cannot see it yet?
Yes, now it works again. Yes.
Okay, I'm sorry for that. Okay. What I was talking here is, can you just let me know from which slide you weren't able to see anything?
Since you restarted the screen share, we didn't see anything.
Okay. Oh, okay, thank you. Okay, like I'll just very quickly go through it again. This is one of the plots for PM 2.5 concentration. On the x-axis, we have the hour of the day near Beijing, and this is a 15 days data of January 2019. What we see here is, outside of 99.7% confidence interval, we see 11 points. And for some reasons, they look that they may be due to miscorrect reading or anything else. And this method helps us to penalize these values and in a way provide a score for the station. While when we go to another station, which is near London, and this is 15 days in mid-April, what we see is most of the value, like all the values, in fact, lies in between 99.7% confidence interval. And while looking through the data, we also find, like, we came to an observation which we thought was very interesting. And this is the data for mid-April in 2019 and 2020 near Delhi. And what we could see is the mean of the predictions based on this Gaussian process varies by roughly like 20 microgram or maybe 30 microgram per meter cube during this period for 2 different years, while the confidence interval also changed by more than almost like 80 to 90 microgram per meter cube for 99.7%. Why this happened? This is what we came to know. This is mostly the effect of lockdown. And what we see in 2020 is way lower values of PM 2.5 concentration in New Delhi compared to the last year in the same period. And what we are planning to do forward is now to scale this process for the entire world, where we'll be going to each station and doing this, which is pretty doable in a sense. Like, these plots don't take much time to generate. We also want to do some other statistical test taking temporal correlation into account once we are able to do this. And in the end, we also want to utilize the the spatial correlation, like how closely this entire process. Mia and Johannes have been always helping us whenever we needed anything, be it technical or more on the scientific perspective. And that's all I have for the presentation. Thank you.
Okay, thank you, Mohit. It was it was a bit sometimes hard to understand due to the technical issues, but I think we understood most of it, and it's quite impressive the work you did already. Due to time constraints, I would just go to the last presentation, but if you have questions, please go to Slido and ask your questions there, and we can come back to any question addressed to Mohit later. And with this, I will invite our last speaker, Milan Klöver, who will present his project Elfridge.jl. Milan, the floor is yours.
Hey everyone, let me just share my screen now. I just realized I have to change some setting. Here we go. Let me check if this works now. Here we go. I think I can just share this one now.
Yes, it works. We can see the presentation.
Yeah, does that work? Perfect. Does it also work if I go in full screen mode?
Yes, perfectly.
Yeah, perfect, great. Yeah, great. So this is my project, which I just like the work in progress title is Elfridge.jl. It's actually a project on climate data compression, and basically it's just this like underlying question of like how do we put an elephant, meaning like large amounts of climate data, into something that is much smaller. Yeah, so I'm a PhD student in Oxford and supervised by Miha and Juan, who I think also are both listening now. So to the two, yes, you will also see some new results. So in terms of compression, data compression, it's always a trade-off. So we could either end up with preserving a lot of information, but then we have something really big. And if we want to compress that down, we either end up in one edge of the trade-off where yes, you have to store a lot of data. You need to buy a big data archive, or you end up in the dilemma that you lose a lot of precision, which you probably don't want to do. Or it's a question of speed, right? So you could, for example, just save your forecast. Your forecast model setup, but then you would need to rerun the whole thing in order to regain the same information. So that's obviously not desirable. And so the question is really, is there something somewhere in between where you have a small amount of data that preserve the precision that you need, and as well that you can like easy read and write this data. So the data that I've been looking at is from the Copernicus Atmospheric Monitoring Service. So that's the CAMS data that was already talked about in the last talk. So we have about 50 air quality variables, so including like nitrogen dioxide, ozone, sulfate, but also aerosols. And at the moment, there is about 9 terabytes produced every week. So that means if you calculate that down, it's basically producing data quicker than, for me, on my internet connection, I could ever download. And the data is also quite, it has a lot of different features because there's a lot of different physical as well as chemical processes going on. So for example, here just showing nitrous dioxide in the stratosphere, and you can see the impact of the sun, as well as you can see some turbulence and winds blowing everything around. Whereas then once you go to the surface and basically in the same data set, just like further down, You can even see ship tracks and then the impact, for example, of industry. And so what I want to tell you in the next 10 minutes are some perspectives for how to compress this data. So currently we're at, and I will talk a little bit about the details of what that means. We're currently at a compression factor of 1.3, meaning that you could store the same data 1.3 times. So there are some solutions that I propose. One is the short-term solution, which I will go into detail, but this is what I call log quantization or log packing. Then there's a medium-term solution, the technique that I call round, combined with lossless compression. And then there's a long-term solution, which is the ZFP algorithm. And you can see the compression factors and how much that actually could benefit it. We will talk a little bit about information entropy, and as I don't know how many of you know or have an intuitive understanding of information entropy, I just provide you a little very quick example to give everyone an idea. So definition of information entropy is basically just you sum up P log P, whereas P is a chance. And so the sum over all these chances should be 1. So if you look at this at a die with 8 sides, and let's roll this die, then the outcome of either 1 or 8 is always 1/8. So if you calculate the information entropy of that, this 3-bit, because the outcome is either, and then you can basically just encode this into into bits 0, 0, 0, 0, 1, and then you basically have all the 8 outcomes, and because they're all evenly likely, the entropy is maximized. So we have actually 3-bit. Now imagine you have actually this die loaded. So that means that some outcomes are always more likely than others. And I've just written down some chances here. If you calculate the entropy for that, you actually end up with something that is only slightly above 2. And the reason is basically because if you roll the die, you basically already know that the first bit will always be 1, because it's super unlikely that the rest happens. And so from an information point of view, you basically don't even have to store the first bit, and you would be well off just storing the remaining 2. That's kind of the idea behind it. And so what is currently done in all these data sets is that a method that is called 24-bit linear quantization. So you basically just take all your values, you look at the minimum of the values, you look at the maximum, and you just divide all the chunks in between into 2 to the power of 24. So that's something on the order of a couple of million steps in between, and then you basically just reassign them, and you basically just number the values. That basically avoids that you encode anything that is larger than any of the numbers that occur in your data set, and that you encode anything that is smaller than that. Sounds like a very intuitive and reasonable idea. The problem is, though, that if you look at how often any of these chunks actually appear, so these ones here, how often any of these appear, you actually see that well, there's a lot of bit patterns happening around occurring around the minimum, but there's basically nothing happening for most of these for these quants in the quantization. So if you calculate the entropy of that, although technically you could have 24, you only end up with 16. So technically you're only using 0.4% of the bit patterns, which is like a very big waste. If you do the same idea, but instead of spreading these quants evenly, but if you spread them in a logarithmic fashion, so here, for example, let's say we don't use 24-bit, we use 16-bit, and you do the same again, and this is again nitrogen dioxide here, you suddenly see, ooh, there is some kind of pattern occurring, and we kind of make use of more or less all of the bit patterns. So if you now calculate the entropy of that, you actually get something much closer to the maximum entropy, which in this case here in this plot would be 16, and we actually end up with 15. So technically we are only wasting 1 bit. You cannot just do this for one variable, but you can actually do that for all of them. So the variable that we've looked at before is nitrogen dioxide. That's the orange thing here up in the middle, and the logarithmic entropy is on the left, whereas the linear entropy is on the right. And you can see that actually for the whole data set, most of these are almost all of the variables, there's a few exceptions up here, where it basically doesn't really matter whether you encode them linearly or logarithmically. Most of them are actually logarithmically distributed. And so it doesn't really make sense to encode them in a linear way. And then already one thing to bear in mind is that, I mean, logarithmic distribution sounds really nice and sounds really nice to chuck it in these parts, but actually the floating point numbers that we already start from, they are already approximately logarithmically spaced. And so this is something to keep in mind, because this will be the next method that we'll look at. So we can basically do this now for all of the variables. And you can see the long list here on the left, where you have all these different aerosols. And then there's some alkanes and alcohols along there. There's like the sulfates, blah, blah, blah. And you can look at things like the mean error, absolute error, decimal error. And then I have basically put the linear quantization in black and blue and the log quantization in red and orange. And you can see that actually you could very safely replace the 24-bit linear packing or linear quantization that is currently used by 16-bit. It will be smaller, right? Because you only store 16-bit per value, and you have very much comparable errors. And some of these errors, especially like decimal errors, are actually much better bound, whereas like the maximum errors of these linear packing actually can be quite large. So that sounds like a good technique. However, as I said, floating point numbers are already logarithmically distributed. And so the underlying issue with floating point numbers is that if you have a floating point number, and here I'm just giving like a little example, you have a sign bit here in the front, you have the exponent bits, you have the significant bits. The point is that many of these significant bits actually do not contain real information. However, they appear to be more random. And so if you want to compress that, compressing noise is very, very difficult, because there's no underlying pattern to it. And so basically, these bits here basically has almost full entropy. And so you actually have to actively chunk them away. You somehow have to delete them. And you can do this, for example, by rounding. So if you round this number here, then, okay, you have a little carry bit here that goes over, but otherwise all of them are 0. You introduce a little error. But basically, this is much easier to compress, because if everything is 0, then it's quite easy to remember. And I just show this here. So let's say you have some kind of, it's often called then in data compression a 1D bit stream, so just like a long chain of floating point numbers. And if these are your floating point numbers, what you can do is that you basically just somehow round away the non-significant bits here at the end. You have some rounding happening here, and then because we're looking at climate data, and we always have some kind of correlation in space and time. And if we unfold this into like a 1D bit stream, then we could think of this either like going along the longitudes or latitudes first, or in the vertical first, or in time, whatever. But you will have some kind of correlation. So always knowing what your value is, your next grid point will be very, very close to that. And so you can basically, the idea of this, and this is what I call the round plus lossless compression, is you round this is correlated. So actually what if you want to compress that, you only have to remember the first bit here, then the bit that is different for every value, and then you have to remember the last bit. And so going from 160 to 60-bit down, you see that there's already big compression happening. To generalize this idea of a 1D bit stream, this is basically what's exploited by the ZFP compression. So instead of just looking at a single one-dimensional array, you can do this also for like 2 to up to 40 arrays. And here's an idea of like a 3D array, where you basically just chunk up everything into small blocks. And then you basically do the same technique in these small blocks. But then the idea is that the values inside such a block are very well correlated and therefore very compressible. And so this is just an example here from the ZFP website, where this chunking into blocks, once you have really high compression ratios, becomes evident here. However, if you have like medium compression ratios, then you see actually you can't really detect these underlying blocks. So summarizing all of that, this is now the absolute error and the decimal error for all of the variables in the CAMS dataset. And the linear quantization, as before, only has a compression factor of about 1.3. So the compression will always end up down here, with errors widely spread depending on which variable you actually look at, and especially the decimal error can have really, really big values in this linear compression. If we would go to logarithmic quantization, because we're only using 16-bit now, for example, we actually end up with a compression factor of 2, and the decimal, especially the decimal, we would gain that the decimal error is much better bound than it was before. If we want to go to even higher compression factors, so like round plus lossless here, basically on average reaches a compression factor around factor of 10, something between, let's say, 10 to 15, depending on the variable. Some variables are very, very well compressible. Some others are not that much. Yes, we would need to take into account that the absolute error would be slightly larger, but it's still well bound, and having something on the order of, like, I don't know, a few % error, I think that is, I mean, I would need to talk to the presenter of the last presentation what actually the errors are in the observations, but we have still, this is still well bound. And then especially the decimal error, we only get like a decimal error of, let's say, again, like a 1% or so. There are a few outliers here, but it's definitely way better than where we are currently are. So basically going back to the timeline, as I said before, so uncompressed, this is what we currently are, and this is basically where we can get with these different techniques. To make this all a bit more visual and to aid people to understand what's actually happening here, basically just plotted this on a globe with the compression factor, so uncompressed on the left, and then we have another slice here of and then increasing compression factors for this round plus lossless technique. And you can easily end up, you can see here, once you have the compression ratio too high, it looks a bit like a comic. So that's definitely not what we want, but having something here on the order of factor of 10 or so, this is definitely feasible. And I would believe that everyone's very happy to work with this data. For ZFP, because of making use of the 3-dimensional structure of the data, you could probably even end up here, let's say this slice here with like 40 times compression for this. In this example, this is ozone. If you would go too high with the compression, you can see this. You can see here again this block structure appearing, and that's definitely not what we want. But like compression factors between 20 and 30 are definitely possible. So just to summarize that. Currently, let's say we have 1 gigabyte of this data set, and if it was uncompressed, yep, here 1 gigabyte. What we currently are, we're compressing it down to like 750 megabyte. Short-term solution is the log packing or the log quantization, which reduces this data set down to half of that. And then if we actually like medium turn is this round plus lossless, where we end up here with like something on the order of 70 megabyte. And if we actually would exploit the ZFP algorithm, then we basically can compress the same data set down to 30 megabyte. So if you find that interesting, just you can check out the repository. I will definitely in the next month update that so that all of this information is nicely viewable in the README. You can always contact me. You can find me on GitHub as well as on Twitter, and I'm happy to take any questions. Thank you.
Thank you, Milan. This is, I think, not only for CAMS data of high importance, but in the era of big data, I think very, very important work you do. I would like to go now over to the questions, and for this I share my screen and open up Slido. Moment. Okay, and there's actually already one question from Pedro to you, Milan. You mentioned data is time and space correlated. Are you exploiting the fact it is correlated in space in both latitude and longitude, 2 dimensions? Yeah, so with the round plus lossless, because the lossless compression algorithms that are used there are basically like off-the-shelf algorithms that are used, for example, also in like text compression or in audio compression. You're basically, what you're compressing is a 1D vector. So if you start with a, let's say, 2D field or 3D field, you somehow have to unravel that, right? So you could, for example, walk along the longitudes and the latitudes first, and then the vertical, or in any other kind of permutation. So in that sense, no, you're not making use of more correlation than just in 1 dimension only.
in order to make use of the correlation in both, let's say, all space dimensions as well as time, as well as, for example, you could think of ensemble members, you would really need to use the ZFP algorithm. And yeah, so that's exactly the reason why the ZFP is so much better than the round pass lossless.
Okay, thank you. We have also a question for Ayush, which we didn't respond yet. So Ayush, is a question also from Pedro. Is your project going to add Python bindings to OpenIFS?
Yeah, as a part of
it is, Ayush, excuse me, it is very hard to understand you. There's also a lag.
I can take this one if you want. Hi, this is Michael. I'm one of the supervisors. So it's not necessarily Python bindings that we're using. It's a wrapper package that I've written. That's basically Python based that just executes OpenIFS from kind of known presets. So in that sense, it kind of is. It's also the same thing that underpins Tiberius project. So and yeah, this is being developed internally actually.
Yeah, thanks, Mike. That was interesting.
Okay, thank you, Michael and Ayush. There's also one question to Mohit from SAC. So that looks like a really nice way of identifying outliers in the data. I'm wondering if or how it can help to distinguish between outliers due to instrument problems versus outliers due to real exceptional pollution events that may be localized in space or time.
Yeah. Like when we are dealing with such a high quality of data, we did think about this. And yes, if there is, for once, our purpose is not to exactly identify one data point, rather we are trying to look into the stations, like if that station is working well or not. So in the way we put in score to our stations, so if that event occurs many times, then then what will happen is, like, if there are very high values many a times, which may be due to sensor or any other technical fault, then we will put that station as a kind of a red station or station which we have to look into. But yes, if once or twice just there are very high values, we are not going to penalize our station that much. So yes, at a global scale, it is very difficult without looking into one particular station, that whether it's a high event or it's a technical fault. But in the end, it will help us to summarize whether a station might have more of a technical fault or is it just a high value.
Okay, thank you, Mohit. Okay, so far we don't have any questions anymore. I would like to, before we close, because we already a bit over an hour, I would like just to thank everyone for your time today, even it was a bit longer than anticipated. Thank you to the speakers for the presentations and the great work and the projects, and we're already excited to see the full results on 16th of October. And this is also what I would like to point out. So for all the attendees today, if you're interested in a follow-up of the project results you've heard and seen today, so please save the date. On 16th of October 2020, we will organize the final ECMWF Sum of Weather Day as Weather Code Day, and this will be the chance to get or to hear about the results of all the 10 projects of ESoC this year. For updates on this, we ask you to follow us on Twitter, or you can also go to our website esoc.ecmwf.int. And as already the project teams today showed you, ESoC is about open source development. So please go to github.com/ESoC. You can go to challenges_2020 and you see an overview of the projects. And then each project is also has their own repository, and you can also follow all the open source developments there. And yes, with this, thank you again, everyone, for joining today. And yes, I wish you a nice day, evening, or morning. Thank you and goodbye.